models? What's your sort of focus?
The work that I do in the Antarctic sort of been along a couple of tracks. As a graduate student, I got involved with the Automatic Weather Station project, and I was looking at katabatic winds in the Antarctic. So these are the strong winds that drain off the interior of the continent and down to the slope. As a master's student, I was looking at them with observational data from the automatic weather stations, and in doing my research, I became frustrated that we had, a handful of points of observations and just at the surface, and you could draw some conclusions about what was happening, but you had this big void. You had to guess what else was going on. And one of the members of my master's thesis committee suggested that I should think about working with computer models. And if you're using a computer model that's producing a reasonable representation at the points where you do have observations, then you might have some confidence to say, well, I'm going to use the model data where I don't have observations to sort of fill in the gaps and give me a sense of the three-dimensional structure of the atmosphere that I don't get from the observation. And so that's how I started working on computer models. And I moved from the University of Wisconsin to the University of Wyoming for my PhD. Worked with a professor there, Tom Parrish, who actually was a Wisconsin graduate as well. He got his PhD there. And he was involved in computer modeling in the Antarctic. He had written one of the first atmospheric models for the Antarctic to simulate katabatic winds. And so I worked with Tom using his model, and then using MM5, which was a community-developed model that was provided by NCAR. And so that's how I got started on that. When I finished my PhD at Wyoming, I did a postdoc at Ohio State University, and there I worked on development of a polar version of MM5. The work that I did as a PhD student with MM5, I found that MM5 didn't do a very good job simulating the Antarctic atmospheric state. It had a problem. It simulated too much cloud cover. It didn't simulate the radiative cooling of the surface adequately, and as a result, it didn't simulate realistic-looking katabatic winds. So there are a lot of sort of basic problems with the model, and I worked on finding the source of those problems in the model and fixing them. The model had been developed for mid-latitude use, and so it wasn't surprising that it didn't work well in the polar regions. There are enough differences in terms of what processes are important in the polar region compared to the mid-latitudes that MM5 didn't have that right balance.
Now, from what I understand about the models, there's kind of like a grid that can go over the entire Earth, and then there are different resolutions that the grid can take. So when you talk about developing a polar version of the MM5, does that mean that MM5 is sort of like one grouping of formulas, and then your work would be added onto that, and so it would come into play for the entire global model, or would it be something that's used very specifically for the poles?
There's sort of two classes of atmospheric models. There are global models, which their grid covers the entire globe. And then there are regional models like MM5, where the grid covers just a small part of the planet. And to use those models, you need to specify what's happening on the lateral edges of your domain, and that usually comes from observations or from a global model. And then you can, say, if you're interested in just the Antarctic, running a regional model like MM5 just over the Antarctic saves you a lot of computational time, because I don't need to do calculations over all of my grid points over the entire planet. And it allows me to use a model that has been developed specifically for the region of interest. So I can make sure that the model is representing all of the key polar processes I need, and I don't need to worry about things that aren't important there that might be important in the mid-latitudes or the tropics. And so that's the advantage of a regional model, is that you can tailor it to where you want to work.
So when you work on these models, do you does working on the model give you kind of new insights into the way weather works, or does it go the opposite direction, like you have an idea and then you implement it in a model?
It goes both ways, actually. Initial, sort of when you're first working with the model, the direction of information flow is that you have weather observations, you've run a simulation with your model, and you're comparing what your model has done compared to the observations to see what the model does well, what it doesn't simulate well, where its shortcomings are. And a lot of times you'll use not just the standard meteorological observations, temperature and winds and pressure, but you'll also care about things that help you get at the processes that are acting. So we might have measurements of the turbulent transfer of heat and moisture between the atmosphere and the surface, or the radiative transfer that comes through the atmosphere and comes down to the ground. And in looking at those types of process-based observations, you can get at what processes are not well represented in your model. And so you're really trying to make sure the model has the right processes, and if you do that, you then hope that it gives you a good simulation of the atmospheric state, temperature, and the winds and things like that. And in my experience, that usually works well, that if you make sure the processes are well represented, you then get a good simulation.
So it's kind of like a feedback loop where you're saying, well, this simulation isn't right, and so my processes must not be.
Yeah.
Oh, cool.
And then, once you have a model that you're comfortable with and that you feel is working well, then you can run experiments with that model. You can start to look at what that model is simulating in places where you don't have observations. And then it will provide guidance to say, you know, this is an interesting location where I should be making some observations. And so then you sort of going the opposite direction. You're using the model to direct what types of observations you want to make and where you want to make those observations.
Oh, which is kind of what you're doing here.
Yes.
Oh, great.
Yep.
Gosh, what was I going to ask this? So a lot of people, I think, that are not in the sciences are getting confused about all this talk about simulation models of weather because of the uncertainty and we all know about these kind of political issues that have come into play. What do you think is the thing that people are having the most difficulty understanding, or what's the thing that you wish that people really understood about the science of weather models?
I think there are a few things that when I talk to the general public or teach introductory classes to non-science majors, things that I see that are misconceptions. One is sort of lumping weather forecasting and climate prediction together, and they're related problems, but they also are different. For weather prediction, it's very important to know the initial state of the atmosphere, and you need a good estimate of that initial state to make a good forecast. And the atmosphere is the physical laws that govern the way the atmosphere works are chaotic, in that a small change in the initial conditions can at future times lead to a large change in what you're predicting is going to happen. And because we never know the exact state of the atmosphere, we're not making measurements at every point. Our measurements have errors in them. Our forecasts are always the computer models are always being started with a non-exact initial state, which means that at some future time, that forecast isn't going to be right because those small differences from reality will grow into a big difference.
Sure.
And so that limits how long we can make an accurate weather forecast. So you don't typically see weather forecasts made out more than about 10 days. That's the limit of predictability that's imposed with the level of observations we have and imposed by the physical laws that govern how the atmosphere works.
But hasn't it been getting better?
It has. And that's the improvements in weather forecasting have come from two things. One, better observations. So the addition of more and more satellite data that fills in sort of the data voids and gives us a better three-dimensional picture of the atmospheric state. And the second is through research, where we better understand the processes that are acting in the atmosphere and then can include those processes in our computer models so we can make a better forecast.
But you're saying that's going to be exhausted at some point, and I've heard this from a meteorologist.